Hi, it's Mohammed Fareed. Today I'm going to talk about the artificial blood vessel. Moving on, the blood vessel carry blood around the body. There are three types of blood vessel. One is arteries, carry blood from the heart to different parts of the body. Two is veins, carry blood back to the heart. Three is capillaries, carry blood to the tiny areas like corona. Problem statement. Millions of people die of cardiovascular disease every year. Heart failure, tachycardia, coronary artery disease, etc. Blood thinners are the major medicines given, which is not a cure. Majority of these deaths can be stopped with a blood vessel replacement. Solutions. So the solutions are biological blood vessel are inactive for medium and large caliber applications. Development of artificial blood vessel is a promising solution. Biological blood vessels, there are arteries or veins extracted from donors to implanted into the patient. Biological grafts often fails due to rejection by the recipient. Biological blood vessels are inactive for medium and large caliber application due to clot, cell death, etc. They do not always come in the size and shape that the recipient needs. Here is, of course, our artificial blood vessel project, but in reality, this is the artificial blood vessel in reality plugged into the veins to be able to flow blood quickly to the heart. So here, moving further, artificial blood vessels are tubes made from synthetic chemically produced materials to restore blood circulation. History goes back to a previous material called Vinion being tried on dogs by Voorhees on humans in 1953. Once inserted, human cells grow over them and they become part of the body, can be manufactured in any size and shape needed. Different materials can be tried as per the strength required. Objectives. So the objectives of this project is to find out 3 suitable materials to fabricate artificial blood vessels, to find 3 different diameters of actual blood vessel present in the human body, and normal thickness. I actually found 1 diameter and I used 1 diameter for 3 different lengths. So design prototypes of blood vessel using the diameter data found with length 1, 10, and 100. Perform simulation based on blood flow velocity and normal human blood pressure to find the stress on the walls of these designed models. Perform a failure study of a blood flow rate of 5 times the normal rate. Moving on, so the materials I selected is nylon 6 because it's biocompatibility, fast degradation, and can be used alone. PET, less bleeding, low permeability, low viscosity, and PTFE, stability, durability, and costly. Based on diameters, blood vessels can be classified into 3 things or three things, yeah. So it can be small, medium, and large. Small caliper, medium caliper, and large caliper. Small caliper is less than 6 millimeters. Medium caliper is from 6 millimeters to 9 millimeters. Large caliper are greater than 10. Based on these, blood vessel for each category was selected. The diameter selected is 2 millimeters, as I mentioned in the previous slide, with length of 1, 10, and 100 for each material selected. This is the prototyping. I used SolidWorks 2018, and this is the prototype. This is the dimension and the model. Step 4, simulation. So, of course, I mentioned in the previous slide that I used SolidWorks. So for simulation on the model, the boundary conditions were for the blood velocity was 26 milliliters per minute, and then we had the flow rate of 4.3 times 10 to the power of minus 7 meters cube per second, and flow rate of 2.167 times 10 to the power of minus 6 meter cube per second. The second one is actually 5 times the actual one, which is 4.33 times 10 to the power of minus 7 meter cube per second. And the human blood pressure is 150 millimeters Hg. Human body is 310.15 Kelvin. Moving on, the results. So my results is nylon 6 showed the best results of all three materials and all three lengths, 110 and 100, with diameter of 2 millimeters. 1 millimeter shear max was 1.773 times 10 to the power of minus 6 newtons per meter squared. And when the length was increased, it did a big jump in the 10 millimeter, which was 5.144 newtons per meter squared, and for the 100 millimeters was the best result, which is 5.2 newtons per meter squared. Moving on, for PET showed decent results too, and it showed like a similarity in results, but less than nylon. But it showed the same similarity in length that was used for PET was also 1 millimeters and 10 millimeters and 100 millimeters. It showed a max shear stress at 1.6 times 10 to the power of minus 6 Newton per meter squared, and jumped at a length of 10 millimeters to 4.83157 newtons per meter squared. And finally, 5.2735 newtons per meter squared at 100 milliliter. This was a pressure rise at 100 millimeter, which PET showed a good result in the 100 millimeters length as nylon 6. And PDFE was also tested the same way by the same diameter of 2 millimeters as the PET and nylon, 1 millimeter, 10 millimeter, and 100. At 1 millimeter, the max shear stress is 1.5396 times 10 to the power minus 6 newtons per meter squared, and increased at 10 millimeters at 45673 newtons per meter squared. There was no any pressure drop. It was constant when the length was increasing. So when the length was increasing, actually the pressure increased, so it gave better results. And in conclusion, this is my table. My table with 2 millimeters of diameter, length of 1, 10, and 100, and my biomaterials are nylon, PDE, PDFE, and here's my max shear stress, which I talked about in previous slide, and max shear strain. In conclusion, nylon 6 gave better result in all three lengths, 1, 10, and 100. Overall, it gave a better result between both PET and PDFE. It showed better results with better flow rates at 5 times the actual flow rate, which is 4.33 times 10 to the power of 7 meters cubed per second. It showed pretty much the results were the same for almost identical for the 5 times rate of 4.33 times 10 to the power minus 7 meter cubed per second, which is 2.167 times 10 to the power of 6 meter cubed per second. Followed by PET was the second best material, and then PDFE was the last one. Moving on, the challenges in this design is artificial blood vessels cannot be used for caliperies. Small caliper application always cause blood clots. Thrombogenicity is always a risk factor. Even a large caliper blood vessel has a 15 to 20% chance of blood clot. Blood vessels could fail inside the body due to a number of reasons like degradation and corrosion. Economic aspects. So out of the three, nylon is the most efficient and cheapest. It is around $2.3 per kilogram. Second is PET, which is $6 per kilogram. For PDFE is $15 per kilogram, which makes it the most expensive. New composites are expected to bring the prices down, are expecting to bring the prices of PDFE down in the future. And this is because PDFE has a long life cycle than both nylon and PET, and its expansion and various time of uses during human operations. So it can be expanded and used various times in a human operation. That's what make PDFE more expensive than nylon and PET. The high demand in Europe, American, and Chinese market is supposed to enhance production, and thereby that's their plan to bring down the cost of PDFE. Future scope: laser treatment to correct the damaged blood vessels, new materials like siliconized rubber and polyethylene blood vessels shows promising results. Tissue engineering to construct biological substitute of recipient blood vessels. The tissue culture will be done on an artificial grass over which the tissue will grow. Tissue 3D printing of blood vessels of artificial scaffolds will be completely replaced. Artificial blood vessel fabrication in the future. There would be no chance of rejection as the cells would be extracted from the recipient itself. These are my references for my research. Thank you for watching and have a good day.